There's a planet out there where it rains liquid iron, another world darker than coal, absorbing almost every photon that touches it. And somewhere in the cosmos, a gas giant orbits two stars simultaneously, while another completes its entire year in less than 8 hours. These aren't fever dreams or science fiction concepts. They're real worlds we've discovered, and they're forcing astronomers to rewrite everything they thought they knew about how planets form and survive. Since the early 1990s, we've confirmed over 6,000 exoplanets. That number grows almost weekly. What started as a trickle of discoveries has become a flood of bizarre revelations. We expected to find solar systems like ours, orderly and predictable. Instead, the universe handed us chaos wrapped in mystery. The story begins with an assumption that turned out to be spectacularly wrong. For decades, scientists believed our solar system represented the standard template. Rocky planets near the star, gas giants farther out, everything arranged in neat circular orbits. It made sense. Our theories of planetary formation predicted exactly this arrangement. Gas giants needed to form beyond the frost line, that magical boundary where temperatures drop low enough for volatile compounds to freeze. Jupiter sat comfortably in its expected zone, and we assumed every system would follow similar rules. Then we found 51 Pegasi b. This world shattered our cosmic confidence. Discovered in 1995, orbiting a sun-like star about 50 light-years away, 51 Peg b was a gas giant. Nothing unusual there, except it orbited closer to its star than Mercury does to our sun. Its year lasted just over 4 days. The planet's surface temperature exceeded 1,000 degrees Celsius. This shouldn't exist. Our models said so. Gas giants can't form that close to their stars. The radiation would prevent it. The material needed to build such worlds simply isn't available in the scorching inner regions of stellar systems. Yet there it was, impossible and real. Astronomers scrambled to explain it. Maybe the planet formed farther out and migrated inward, but how? Why? The discovery of 51 Peg b created a new category, hot Jupiters. And as our detection methods improved, we found more, many more. These worlds weren't rare cosmic accidents. They were common, challenging every assumption about planetary system architecture. Hot Jupiters opened our eyes. Once we knew what to look for, the universe revealed its true strangeness. Take WASP 76b, located about 640 light-years from Earth. This world redefined hellish. On its day side, temperatures soar past 4,000 degrees Fahrenheit, hot enough to vaporize iron. The metal doesn't just melt, it becomes atmospheric vapor, a gaseous cloud of iron atoms floating through the sky. The planet is tidally locked, always showing the same face to its star, just as the moon does to Earth. This creates a permanent day side and night side. The temperature difference between these hemispheres is staggering. The day side reaches 2,400 degrees Celsius. The night side cools to a comparatively frigid 1,500 degrees. That 1,000-degree differential drives winds of unimaginable violence, racing across the Terminator line at 18,000 kilometers per hour. Here's where it gets genuinely weird. Those winds carry vaporized iron from the scorching day side to the cooler night side. As the metal vapor crosses into the darkness, it condenses, it rains. Liquid iron droplets fall through the atmosphere like a twisted metallic thunderstorm. When morning comes to any given location, the iron has already fallen. We don't see the vapor returning. It's a one-way weather system, constantly redistributing molten metal across the planet's surface. You'd think iron rain represents the peak of atmospheric insanity. Then you meet HD1897333b. This planet sits roughly 65 light-years away in the constellation Vulpecula. From Earth, it appears as a pleasant blue dot, reminiscent of our own world. That resemblance is deeply deceptive. The blue color comes from silicate particles in the atmosphere, tiny fragments of what we'd call glass. The temperature exceeds 1,000 degrees Celsius, and the winds, those beautiful, terrible winds, howl at 7,000 kilometers per hour, 7 times the speed of sound. Those silicate particles don't float peacefully. The extreme heat vaporizes them on the day side. The supersonic winds carry this glass vapor to the night side, where it condenses. It rains glass, but the wind doesn't stop. The glass doesn't fall straight down. It cuts horizontally through the atmosphere at speeds that would make a bullet jealous. Imagine standing in a hurricane made of microscopic glass shards, traveling at 7,000 kilometers per hour. Actually, don't imagine that. It's too horrifying. The violence of these worlds forces a question. How do they survive? The radiation, the tidal forces, the atmospheric chaos, all of it should tear these planets apart. Yet they persist, orbiting their stars year after impossible year. WASP-12b offers a grim answer. It doesn't survive. Not permanently. Located 600 light-years away in the constellation Auriga, this doomed world spirals slowly toward destruction. The planet orbits so close to its star, the tidal forces stretch it into an egg shape. The star's gravity doesn't just pull on WASP-12b, it actively deforms it, creating massive tidal bulges. The intense radiation heats the planet's atmosphere until it swells beyond the planet's ability to hold it. Material streams away into space, bleeding off into the void. Scientists estimate WASP-12b has about 3 million years left. That sounds like a long time. On cosmic scales, it's an eye blink. This planet is being consumed, slowly devoured by its own star. We're watching a death in slow motion, witnessing the final act of a world that ventured too close to the fire. But not all bizarre exoplanets are suffering. Some are just deeply, profoundly strange. TAR-ES 2b, sitting roughly 750 light-years from Earth, holds the title of darkest known planet. It reflects less than 1% of the light that hits it. Coal reflects more light. Black acrylic paint reflects more light. This world absorbs photons with unnerving efficiency, making it darker than anything we've encountered in our solar system. Why? The planet orbits close to its star, heated to around 980 degrees Celsius. That rules out reflective clouds, the kind that make Jupiter and Saturn shine so brightly. But temperature alone doesn't explain the extreme darkness. Scientists suspect the atmosphere contains light-absorbing chemicals, possibly vaporized sodium, potassium, or gaseous titanium oxide. These compounds grab incoming photons and refuse to let go, turning the planet into a cosmic black hole for visible light. it's not completely invisible. The extreme heat causes the planet to emit a faint red glow, like a lump of coal in a dying fire. But if you could somehow stand on its surface, you'd see almost nothing. The planet would absorb the light around you, creating a darkness more complete than any night on Earth. Then we have the opposite extreme. LTT9779b, located about 260 light-years away, reflects 80% of incoming light. It's the most reflective planet ever discovered, a cosmic mirror hanging in space. The secret lies in metallic clouds surrounding the planet, composed of silicates and titanates. These clouds act like billions of tiny mirrors, bouncing light back into space with remarkable efficiency. The planet shouldn't exist. It orbits extremely close to its star, close enough that stellar wind should have stripped away its atmosphere millions of years ago. Yet the atmosphere persists. Scientists believe the metallic clouds are too heavy for the stellar wind to dislodge. The very thing that makes the planet reflective also protects it from destruction. It's a cosmic accident of chemistry that allows this world to survive where others would have been scoured clean. Darkness and reflection represent extremes of appearance. But what about substance? What happens when you build a planet from the wrong materials? Enter 55 Cancri A, the so-called diamond planet. Discovered in 2004, this super-Earth orbits a sun-like star about 40 light-years away. Its mass is roughly 8 times Earth's. Its radius is double ours. But its composition tells a very different story. The host star is carbon-rich, and the planet inherited that chemistry. Scientists analyzing its mass, radius, and stellar composition concluded the world is made primarily of carbon, not carbon dioxide or organic compounds, but crystalline carbon, diamond and graphite. At least a third of the planet's mass might be pure diamond. The surface temperatures exceed 1700 degrees Celsius, hot enough to melt iron. The planet completes an orbit in less than 18 hours. Imagine a world where the ground beneath your feet is compressed carbon, where the mantle contains diamonds the size of mountains, where the entire planet is essentially a massive gemstone baked to glowing temperatures. The discovery captured public imagination immediately. A diamond planet. The implications for planetary science were profound, but let's be honest, everyone was thinking about the value. Later research complicated the picture. Some scientists now suggest the planet might be rich in aluminum oxide instead, making it more of a sapphire world than a diamond one. Either way, it's not made of the familiar silicates that dominate rocky planets in our solar system. It's fundamentally different. A planet built from exotic materials we barely understand. These worlds challenge our assumptions about composition. But what about structure? What happens when a planet doesn't follow the density rules? The Kepler-51 system, located roughly 2,600 light-years away, hosts 3 of the strangest planets we've found. They're called superpuffs, though cotton candy planets is the more evocative nickname. These worlds are roughly Jupiter's size. Their mass, only a few times Earth's. The density, less than 0.1 grams per cubic centimeter. For comparison, Saturn, our least dense planet, clocks in at 0.69 grams per cubic centimeter. These worlds are lighter than styrofoam. How is this possible? Planets have massive hydrogen and helium atmospheres, so bloated and extended that they dominate the planet's volume. The solid core, if one exists, represents a tiny fraction of the total. These aren't gas giants like Jupiter. They're something else entirely, worlds where atmosphere overwhelms everything else. The mystery deepens when you consider their survival. These extended atmospheres should be vulnerable to stellar radiation, gradually stripped away over time. Yet the planets persist. They're young on cosmic scales, which might explain it. These worlds might be temporary, slowly losing their puffy atmospheres until they shrink to more conventional sizes. We might be witnessing a brief phase in planetary evolution, a moment before these giants deflate into something more ordinary. Or maybe we're completely wrong about how they work. That happens a lot in exoplanet science. The discoveries keep coming, each one stranger than the last. Kelt 9b, orbiting its star at a distance closer than Mercury to our Sun, reaches temperatures of 4,300 degrees Celsius on its day side. That's hotter than some stars. The heat literally tears hydrogen molecules apart into individual atoms. When these atoms flow to the night side, they recombine, only to be torn apart again when they cycle back to the day. The planet exists in a constant state of molecular destruction and reformation, its atmosphere churning through an endless chemical cycle. WASP 107b, the size of Jupiter but only a tenth its mass, displays east-west atmospheric asymmetry. One edge of the atmosphere behaves fundamentally differently from the other. We don't have anything like this in our solar system. The extreme puffiness and low gravity create conditions we're still trying to understand. Then there's GJ1132b, a rocky world that might have lost its original atmosphere but grown a second one through volcanic outgassing. If confirmed, this would prove planets can experience complete atmospheric regeneration, replacing one atmosphere with something entirely new. It's planetary reincarnation, a second chance at habitability. Every discovery raises new questions. How do hot Jupiters migrate inward without being destroyed? Why do some planets develop metal clouds while others absorb all light? What determines whether a world becomes a puffy giant or a compressed diamond? The more we learn, the more we realize how little we understand. And we haven't even discussed the truly weird ones yet. The planets that orbit dead stars, the worlds with backwards orbits, the rogues tumbling through interstellar space with no star to call home. The universe is stranger than we imagined. It's stranger than we can imagine. These bizarre exoplanets aren't exceptions or outliers. They're the norm. Our solar system, with its orderly arrangement and familiar planets, might be the cosmic oddity. We built our theories on a sample size of one, then acted surprised when reality refused to cooperate. But here's what really keeps astronomers up at night. We've only scratched the surface. Those 6,000 confirmed exoplanets represent a tiny fraction of what's out there. Our detection methods favor certain types of planets. The big ones, the close ones, the weird ones that transit their stars or tug them with observable force. The truly alien worlds, the ones that don't fit our search parameters, remain hidden. What else is waiting out there in the darkness? The answer lies in how we find them. Our telescopes aren't neutral observers. They're biased instruments, built by humans with human assumptions about what planets should look like. Transit detection works brilliantly for planets that pass in front of their stars from our perspective. But that's a narrow slice of reality. Imagine looking at our solar system from a random angle in space. Would you see Jupiter transit the Sun? Probably not. The odds are against it. And if you can't see the transit, you can't use transit detection to find the planet. Radial velocity detection measures the wobble a planet creates in its star. But tiny planets create tiny wobbles. Rocky worlds the size of Earth, orbiting at comfortable distances, barely register. We're essentially blind to them, unless we get very, very lucky. Direct imaging requires planets to be large, bright, and far from their stars. Close-in planets drown in stellar glare. Small planets don't emit enough infrared light. We can only photograph the monsters orbiting in the outer darkness. This creates a profound selection bias. We've found the strange ones because strange is what our methods can detect. The normal ones, if they exist, remain hidden. PSRB 1, 2, 5, 7, plus 1, 2b represents one of those early discoveries that should have warned us. Found in January 1992, it became the first confirmed exoplanet. And it orbits a pulsar. A pulsar is a neutron star, a stellar corpse spinning hundreds of times per second, blasting radiation across space with each rotation. These are not gentle places. The process of becoming a neutron star involves a supernova explosion so violent it should vaporize any orbiting planets. Yet there they were, 3 planets circling the dead star, detected through timing variations in the pulsar's radio signals. PSR B1257 plus 12. B is the smallest, the lowest mass exoplanet ever found. It's barely twice the mass of our moon. How did these planets survive the supernova? They probably didn't. They formed afterward, coalescing from the debris ejected during the star's death. Second-generation planets, born from ashes, orbiting a cosmic lighthouse that shouldn't have planetary children. Only 0.5% of pulsars are thought to host planets. The formation process remains unclear, but these worlds exist, defying our expectations about where planets can form and what events they can survive. Then there's TOI 6894b, announced in June 2025. Its existence poses a fundamental problem. The planet orbits a red dwarf star, roughly 20% the size of our Sun. Red dwarfs are the universe's most common stars, making up about 70% of all stellar objects. They're small, cool, and miserly with their energy output. TOI 6894b is almost as large as Jupiter. According to our best theories of planet formation, this shouldn't be possible. Small stars don't have enough material in their protoplanetary disks to build giant planets. The math doesn't work. The physics doesn't allow it, but the planet exists anyway. LHS 3154b presents the same problem. 13 times Earth's mass, orbiting a star 9 times less massive than the Sun. These are impossible worlds that refuse to acknowledge their impossibility. Astronomers are scrambling to revise their models. Maybe planet formation works differently around red dwarfs than around Sun-like stars. Maybe we've fundamentally misunderstood how protoplanetary disks distribute their material. Maybe planets can migrate from distant orbits through processes we haven't imagined. Or maybe our theories are just wrong. That's always an option. 2. M1510 ABBB takes strangeness to another level. It's a circumbinary planet, orbiting not one star but two. That alone puts it in rare company. Only 16 confirmed circumbinary systems exist, but these aren't stars. They're brown dwarfs, failed stars that never achieved the mass needed to sustain nuclear fusion. They're stellar wannabes, neither planet nor star, but something in between. Finding a brown dwarf binary is unusual. Finding a planet orbiting one is extraordinary. The planet's orbit is polar. It loops over the top of the brown dwarfs, perpendicular to their orbital plane. Imagine the solar system with a planet orbiting through the north and south poles of the Sun instead of around the equator. That's what's happening here. This is the first polar circumbinary planet ever detected. Astronomers suspected they might exist because we've found protoplanetary disks in polar orientations. But finding the actual planet confirms something remarkable about how planetary systems can assemble themselves. The gravitational dynamics involved are nightmarishly complex. The two brown dwarfs orbit each other, creating a shifting gravitational landscape. The planet threads through this chaos in a stable orbit that shouldn't work according to simplified models, yet it does. WASP-107b continues the theme of atmospheric impossibilities. It's Jupiter-sized, but only 1/10 Jupiter's mass. The extreme puffiness creates an extended atmosphere with incredibly low density. Detailed observations revealed east-west asymmetry in the atmosphere. One edge behaves fundamentally differently from the other. We don't see this anywhere in our solar system. We don't fully understand how it happens. The low gravity means the atmosphere is more inflated than any other known exoplanet. It's like a planetary balloon, expanded to the edge of stability. Stellar radiation should strip away such a fragile atmosphere, but the planet persists. This creates unprecedented opportunities for atmospheric study. The extended atmosphere allows light to penetrate deeper than normal, giving us clearer spectroscopic signals. We can analyze the chemical composition in detail, watching how different layers interact and flow. But every answer raises new questions. Why is the asymmetry there? How does the atmosphere maintain itself against stellar wind? What's the source of the inflation? GJ1132b might have experienced planetary reincarnation. Initial studies suggested it began as a mini Neptune, a world dominated by thick hydrogen atmosphere. Then it lost that atmosphere entirely, stripped away by stellar radiation. But the story doesn't end there. Volcanic outgassing might have created a second atmosphere, completely different from the first. If confirmed, this would prove planets can experience total atmospheric replacement during their lifetimes. The planet orbits a red dwarf star. These small, cool stars live for trillions of years, providing vast timescales for atmospheric evolution. A planet might go through multiple atmospheric regimes over its lifetime, shifting from hydrogen to carbon dioxide to nitrogen as geological and stellar processes reshape its envelope. This challenges our assumptions about habitability and atmospheric stability. A dead world might resurrect itself. An airless rock might grow a new atmosphere. Planetary evolution isn't a one-way street toward either habitability or desolation. HR 5183b presents orbital eccentricity so extreme it borders on the absurd. The planet is 3 times Jupiter's mass, orbiting its star every 74 years. That's already unusual, but the orbit itself is the real story. It's egg-shaped, highly elliptical. The planet loiters at the outer edges of its system for decades, barely moving. Then it plunges inward, slingshotting past its star at tremendous velocity before swinging back out to the distant reaches. At closest approach, it comes 10 times closer to its star than Mercury gets to our Sun. At its farthest point, it reaches Earth's orbital distance. This creates wild temperature swings as the planet alternates between freezing and roasting. The orbit is retrograde. The planet moves in the opposite direction to its star's rotation. Almost every known planet orbits in the same direction as its star spins. This is a fundamental prediction of planet formation theory. Gas and dust in a protoplanetary disk orbit in one direction, and planets that form from that material should inherit that motion. HR 5183b breaks this rule. Something violent happened in this system's past. Maybe a near collision with another planet. Maybe a close encounter with a passing star. The planet's orbit bears the scars of some catastrophic event. Astronomers believe it's migrating inward. Over millions of years, tidal interactions with its star will circularize the orbit, gradually transforming this eccentric wanderer into a conventional hot Jupiter. We're witnessing planetary migration in progress. WASP 12bd won't have millions of years. It has roughly 3 million years left before it dies. That sounds like a long time by human standards. In cosmic terms, it's the blink of an eye. The planet orbits so close to its star that tidal forces are tearing it apart. It's wobbling and distorting, stretched into an egg shape by gravitational stress. Intense stellar radiation has caused the planet to swell, making it vulnerable to further tidal destruction. The star is slowly consuming the planet, accreting material from its outer atmosphere. WASP 12b is spiraling inward, closer with each orbit, doomed to eventual destruction. This isn't theoretical. We can measure the orbital decay. The planet is falling into its star at a measurable rate. Future astronomers, if they exist, won't see WASP 12b. It will be gone, vaporized, and absorbed. Similar doomed worlds exist throughout the galaxy. WASP 121b orbits its star in just over 24 hours. It's tidally locked, one side always facing the star. The temperature difference between day and night drives winds exceeding 16,000 kilometers per hour. It's hot enough to vaporize iron, aluminum, and titanium. These metals exist as gases in the atmosphere, creating exotic chemistry we can barely model. The planet is an atmospheric laboratory operating under conditions we can't reproduce. These ultra-hot Jupiters represent planets in their final death throes. They're the last gasps of worlds that migrated too close to their stars and paid the ultimate price. LTT 9779b survived where others didn't. It orbits even closer to its star than many doomed hot Jupiters. Its atmosphere should have been stripped away long ago. Instead, it's the most reflective planet ever discovered. 80% of incoming starlight reflects off metallic clouds in its atmosphere. The clouds are made of silicate and titanate, essentially glass and titanium salts. They've turned the planet's sky into a mirror. The metals might be too heavy for stellar wind to blow away, While lighter elements escape to space, the heavy metals remain, creating permanent cloud layers that protect the rest of the atmosphere. It's atmospheric armor made of glass and metal. This stands in stark contrast to Tres 2b, the darkest planet known. That world reflects less than 1% of incoming light, darker than coal or black acrylic paint. Something in its atmosphere absorbs nearly all light that hits it. Vaporized sodium, potassium, or gaseous titanium oxide might be the culprits. At temperatures exceeding 1500 degrees Celsius, these chemicals exist as gases and absorb light across a broad spectrum. The planet glows dim red from its own heat, but reflects almost nothing. These two worlds represent opposite extremes of planetary albedo. One is a mirror, the other is a void, and neither should exist according to the straightforward models we built. That's the pattern emerging from exoplanet discoveries. The universe doesn't care about our models. It builds whatever physics allows, creating worlds that challenge every assumption we've made about how planets work. Rogue planets don't even bother with stars. They drift through the darkness completely alone. Rogue planets exist without stars, no sunrises, no seasons, just endless cold darkness as they tumble through interstellar space. The James Webb Space Telescope found hundreds of them in the Orion Nebula, free-floating worlds with no gravitational anchor to any star. They shouldn't exist according to what we thought we knew about planetary formation. Planets form from disks of material around young stars. That's the standard model. Remove the star, and you remove the formation mechanism. Yet there they are, hundreds of them, possibly thousands more we haven't detected yet. What's stranger is that about 80 of these orphan worlds travel in pairs. Jupiter mass binary objects, jumbos, two rogue planets orbiting each other as they drift through the void together. Scientists can't explain how they got ejected from their home systems or why they're locked in binary orbits with each other. One rogue planet was measured at roughly 9,950 light-years from Earth. Its mass is about 70 times that of Earth. We detected it by watching it distort light from a distant star as it passed in front. The observation required coordination between ground-based telescopes and the now retired Gaia Space Telescope. That's the only way we could measure its mass and distance. How many rogue planets exist in our galaxy? Conservative estimates suggest billions. Some models predict there might be more rogue planets than stars. They're incredibly difficult to detect because they emit almost no light. No star to reflect, no internal heat source strong enough to make them glow in infrared. They're ghosts moving through the darkness. These worlds challenge everything about how we define what makes something a planet. Does a planet need a star? We've always assumed yes. But if billions of planetary mass objects exist untethered to any star, maybe we need a new definition entirely. PSRB 1257+12b doesn't orbit a normal star either. It orbits a pulsar. This was the first exoplanet ever discovered. January 1992. The announcement changed astronomy forever. But nobody expected the first exoplanet to orbit something as bizarre as a pulsar. Pulsars are neutron stars, the collapsed cores of massive stars after they explode as supernovas. They're incredibly dense. A teaspoon of neutron star material weighs about 1 billion tons. They spin rapidly, sometimes hundreds of times per second. They emit beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beams. The process of becoming a neutron star is violent beyond comprehension. The star's core collapses. The outer layers explode outward at a significant fraction of light speed. Temperatures exceed billions of degrees. The shockwave obliterates everything nearby. Any planets that existed before the supernova should have been destroyed, vaporized, ejected from the system entirely. Yet PSRB 1257+12 has 3 planets orbiting it. How did they survive? They didn't. These planets formed after the supernova from the debris left behind. Second-generation worlds born from the ashes of stellar death. This represents a completely different formation mechanism than the one that created Earth or Jupiter. Only 0.5% of pulsars have planets. The formation conditions must be incredibly specific. You need enough debris left over after the supernova. That debris needs to settle into a disk. The disk needs to be stable enough for planets to coalesce. Most pulsars don't meet these criteria. PSR B1257 plus 12b is the lowest mass exoplanet ever detected. It's smaller than Earth's moon. Finding something that small was extraordinary. The detection method relied on precise timing of the pulsar's radio pulses. As planets orbit the pulsar, their gravity causes the pulsar to wobble slightly. This wobble creates tiny variations in when the pulses arrive at Earth. By measuring these timing variations with extreme precision, astronomers could infer the presence of planets and calculate their masses and orbits. The discovery proved that planets could form in ways nobody had imagined. It expanded the boundaries of where and how planets might exist. If planets can form around pulsars, what other extreme environments might harbor worlds? TOI 6894b shouldn't exist for different reasons. This planet orbits a red dwarf star only 20% the size of our Sun. The planet itself is nearly as large as Jupiter. That combination violates our understanding of planet formation. Small stars don't have enough material in their protoplanetary disks to build giant planets. The math doesn't work. There simply isn't enough gas and dust. Yet here's a Jupiter-sized world orbiting a star that shouldn't be able to create it. The planet was only announced in June 2025. Scientists are still scrambling to explain how it exists. Current theories of planet formation literally cannot produce this result. Something fundamental is wrong with our models. LHS 3154b presents a similar problem. It's 13 times more massive than Earth, but orbits a star 9 times less massive than the Sun. The star is too small. The planet is too large. The ratio is impossible according to standard formation theory. These discoveries force astronomers to reconsider fundamental assumptions. Maybe planet formation doesn't work the way we think. Maybe there are formation mechanisms we haven't discovered yet. Maybe the rules we derived from studying our solar system don't apply universally. To M1510 AB. B takes impossibility to another level. The designation tells you immediately this world is special. It's a circumbinary planet. It orbits 2 stars at once. About 50% of stars in the Milky Way exist in binary systems. But having a planet orbit both stars is rare. only 16 circumbinary systems have been discovered. This particular binary consists of two brown dwarfs, failed stars that never accumulated enough mass to ignite hydrogen fusion. Having planets around brown dwarf binaries is exceptionally rare. Only one other system like it has ever been found. The planet orbits on a polar trajectory. It loops over the top of the brown dwarfs at 90 degrees to the plane they orbit in. This is the first polar orbit ever detected around a circumbinary system. How does a planet end up in a polar orbit? Standard formation happens in the plane of the protoplanetary disk. Planets form where most of the material exists. That material settles into a flat disk due to angular momentum. Planets should orbit in that same plane. For a planet to achieve a polar orbit requires something dramatic. Maybe gravitational interactions with other planets ejected it from the original plane. Maybe the protoplanetary disk itself was tilted. Maybe something disrupted the system during formation. We don't know yet. The existence of protoplanetary disks in polar orientations suggests this might be more common than expected. But actually, finding a finished planet in such an orbit confirms that these systems can remain stable long-term. WASP-107b revealed another unexpected feature. Its atmosphere shows east-west asymmetry. Most exoplanet atmospheres are relatively uniform when viewed from different angles. Temperature variations exist between dayside and nightside on tidally locked planets. But viewing the planet from different directions typically shows similar atmospheric properties, not on WASP-107b. The eastern and western edges of its atmosphere differ significantly. This suggests complex atmospheric dynamics we don't fully understand. Maybe there are massive storm systems. Maybe the atmospheric circulation patterns are more intricate than models predict. The planet itself is bizarre. It's the size of Jupiter, but only 1/10 the mass. That gives it extremely low density and low gravity. The atmosphere is more inflated than any other known exoplanet of comparable mass. The low gravity allows the atmosphere to puff up dramatically. We don't have anything like this in our solar system. No comparison point. No way to test theories about how such atmospheres behave. WASP-107b is a laboratory for studying physics we can't reproduce anywhere else. GJ1-132b might have lost one atmosphere and grown another. Initial observations suggested it started as a mini Neptune, a planet with a thick hydrogen-helium envelope surrounding a rocky core. Over time, stellar radiation stripped away the original atmosphere. The planet should have ended up as a bare, rocky world, slightly larger than Earth. But current observations show it has an atmosphere, not the original one. A new atmosphere created by volcanic outgassing. As the planet's interior remains geologically active, volcanoes release gases that accumulate to form a secondary atmosphere. This represents a completely different atmospheric origin story. Earth's atmosphere formed this way too. Volcanic activity released water vapor, carbon dioxide, nitrogen, and other gases that became our atmosphere. But we didn't think this process could happen on planets that had already lost their original atmospheres to stellar stripping. GJ1132b proves planets can undergo dramatic atmospheric transformations. They can experience multiple atmospheric regimes over their lifetimes. The implications for habitability are significant. A planet that loses its atmosphere to radiation might not be permanently sterile. Given enough time and geological activity, it might regenerate an atmosphere. HR 5183b has an orbit that defies description. Most planets follow roughly circular paths. Earth's orbit is nearly circular. Even Mercury, with the most eccentric orbit in our solar system, maintains a relatively predictable path. HR 5183b doesn't. It's 3 times Jupiter's mass. It takes 74 years to complete one orbit. That alone makes it unusual. But the orbit itself is what breaks all expectations. The planet loiters at the outer reaches of its system for most of its orbital period. Then it suddenly slingshots inward toward its star at high speed before swinging back out again. The orbit is so elongated, it's almost a straight line that bends at the last moment. This creates wild variations in the planet's environment. When far from its star, it's frozen. Surface temperatures plummet. When it swings close, temperatures spike dramatically. Any moons or atmospheric features would experience extreme seasonal variations unlike anything in our solar system. What caused this orbit? Gravitational interactions with another massive planet, probably. 2 giant planets in the same system can gravitationally scatter each other. One might get ejected entirely. The other settles into a highly eccentric orbit. HR 5183b might be the survivor of such an interaction. The other planet might be long gone, ejected into interstellar space as a rogue world. These extreme orbits were common in the early solar system. Jupiter and Saturn likely had more eccentric orbits initially. Over billions of years, gravitational interactions with each other and the asteroid belt gradually circularized their paths. HR 5183b might be young enough that this circularization hasn't happened yet, or it might be locked in this eccentric orbit permanently due to its system's specific configuration. TIC 241249530b has an even more extreme orbit. Its eccentricity is 0.94. To understand how extreme that is, consider that a perfect circle has an eccentricity of 0. A straight line has an eccentricity of 1. At 0.94, this orbit is nearly a straight line that barely curves. The planet swings 10 times closer to its star than Mercury gets to our Sun. Then it travels outward as far as Earth's orbital distance. The temperature swings must be extraordinary. When close, the planet receives intense radiation. When far, it's nearly frozen. The orbit is also retrograde. The planet moves in the opposite direction to its star's rotation. Almost every planet in our solar system orbits in the same direction as the Sun's rotation. That's because they all formed from the same rotating disk of material. Retrograde orbits suggest violent gravitational interactions disrupted the original configuration. This planet is probably becoming a hot Jupiter. The extreme eccentricity causes tidal interactions with the star. Each close approach generates tidal heating. Over time, these tidal forces will circularize the orbit. The planet will settle into a close circular orbit. It will become tidally locked. It will transform into another ultra-hot world like the ones we've already discussed. We're watching planetary migration in progress. This planet won't have this bizarre orbit forever. In astronomical terms, it's transitioning from one type of planet to another. Future astronomers studying this system millions of years from now will see a completely different configuration. PSRJ 2322-2650b represents perhaps the strangest discovery yet. This Jupiter mass planet orbits a neutron star, like PSRB 1257 plus 12b. But this one has characteristics that defy every formation theory. Its atmosphere is dominated by helium and carbon instead of hydrogen. Dark soot-like clouds shroud the entire planet. The extreme pressures inside might compress carbon into diamonds at the core. The planet is stretched into a lemon shape by tidal forces from the neutron star's intense gravity. It completes a full orbit in under 8 hours. That's faster than Earth rotates. The orbital speed must be extraordinary. The tidal forces must be immense. No known theory explains how such a planet could exist or form. Maybe it formed elsewhere and migrated inward. Maybe it's the core of a gas giant whose outer layers were stripped away by the neutron star's radiation. Maybe it formed from supernova debris like other pulsar planets, but with a completely different chemical composition. Scientists are genuinely stunned. The discovery paper couldn't offer a satisfactory formation mechanism. This planet breaks rules we didn't know could be broken. LTT 9779b exists at the opposite extreme of planetary reflectivity, while TRES-2b absorbs virtually all light that touches it. LTT 9779b bounces back 80% of incoming starlight. That's higher than fresh snow, higher than polished silver. This world functions as a cosmic mirror. The planet itself is Neptune-sized. It orbits extremely close to its star. That proximity should have stripped away its atmosphere millions of years ago. Solar wind should have eroded every gas molecule, but the atmosphere remains intact. Scientists found the answer in metallic clouds. The upper atmosphere contains silicate clouds mixed with titanates. These aren't water vapor clouds. They're clouds of vaporized glass and titanium compounds. The metal content makes them incredibly reflective. But here's what makes this truly strange. Those metallic clouds are so heavy that solar wind can't blow them away. Normal gas clouds would be stripped off by stellar radiation pressure. Metal clouds are dense enough to resist. The very thing that makes the planet reflective also protects it from atmospheric loss. The temperature should vaporize those metals completely. But the high reflectivity keeps the planet just cool enough for metallic compounds to condense into clouds. It's a self-reinforcing system. Reflectivity maintains temperature. Temperature allows metallic clouds. Metallic clouds create reflectivity. This world shouldn't exist in this orbital position with this atmospheric composition. Yet somehow all the physics balance perfectly to create the shiniest planet we've ever found. GJ1132 tells a different kind of strange story. This rocky world underwent atmospheric resurrection. The planet orbits a red dwarf star. Initially, it was probably a mini Neptune with a thick hydrogen-helium atmosphere. Stellar radiation stripped that original atmosphere away entirely. The planet became a bare, rocky core. Then something unexpected happened. Volcanic activity generated a new atmosphere. This second atmosphere has a completely different composition from the first. It contains hydrogen sulfide, methane, and hydrogen cyanide. These gases emerge from the planet's interior through volcanic outgassing. This represents atmospheric evolution we've never witnessed before. Most planets either keep their original atmosphere or lose it permanently. GJ 1132b demonstrates that planets can transition between multiple atmospheric states. The original atmosphere came from formation. The new atmosphere comes from geology. The implications stretch beyond this single world. Rocky planets might commonly undergo multiple atmospheric phases throughout their lifetimes. What looks like a dead world today might develop a new atmosphere tomorrow. What has atmosphere now might lose it and gain a different one later. This changes how we think about planetary habitability timelines. A planet doesn't get one shot at having the right atmospheric conditions. It might cycle through several different atmospheric compositions as geological processes evolve. WASP-107b presents yet another atmospheric mystery. This Jupiter-sized world has only 1/10 of Jupiter's mass. It's the least dense planet we've found aside from the super puffs. Recent observations revealed something completely unexpected. The planet's atmosphere shows east-west asymmetry. One side of the atmosphere behaves differently from the other side. This shouldn't happen on a tidally locked world where atmospheric circulation should be relatively predictable. Standard atmospheric models predict strong day-night differences on tidally locked planets. They also predict equatorial superrotation with powerful jet streams, but those models assume rough symmetry between eastern and western hemispheres. WASP-107b violates that assumption. The eastern and western edges of its atmosphere show significantly different properties, different temperatures, different chemical compositions, different cloud patterns. Scientists aren't certain what causes this asymmetry. Maybe the planet has an unusual magnetic field configuration. Maybe there's some atmospheric instability we don't understand. Maybe the low density creates atmospheric dynamics that don't occur on denser worlds. The planet's extreme puffiness makes it an ideal laboratory for studying atmospheric processes. The low gravity means the atmosphere extends far from the planet's surface. Instruments can sample atmospheric layers that would be inaccessible on denser worlds, but that same puffiness creates problems for the planet's long-term stability. The atmosphere is escaping into space at a measurable rate. The planet is literally evaporating. In cosmic terms, it won't last long in its current configuration. TOI 6894b challenges fundamental planet formation theories. This world orbits a red dwarf star. Red dwarfs are the smallest and coolest stars. They have roughly 20% of the Sun's mass. Their protoplanetary disks contain less material than larger stars. The planet is almost as large as Jupiter. It masses 13 times what Earth does. Standard formation models say this combination shouldn't exist. Small stars shouldn't have giant planets. Here's why. Planets form from the disk of gas and dust around young stars. The amount of material available depends on the star's mass. Red dwarfs have less massive disks. There simply isn't enough material to build a Jupiter-sized planet through conventional core accretion. Maybe this planet formed through gravitational instability instead. In that scenario, part of the protoplanetary disk collapses directly into a planet without building a core first. But gravitational instability requires specific conditions. The the disk needs to be massive enough and cold enough. Red dwarf disks typically don't meet those requirements. The discovery of TOI 6, 894b, and similar worlds like LHS 3154b forces astronomers to reconsider everything. Either our understanding of protoplanetary disk masses is wrong, or gravitational instability can occur under conditions we thought impossible. Or there's some completely different formation mechanism we haven't considered. These impossible planets keep appearing. Each discovery narrows the possibilities. Each observation provides new constraints. Eventually, we'll figure out how small stars can host giant planets. But right now, it remains a genuine mystery. Kepler-51 hosts 3 super-puff planets simultaneously. This system takes the cotton candy concept to an extreme. All 3 planets have densities below 0.1 grams per cubic centimeter. For comparison, Jupiter has a density of 1.33. Saturn has 0.69. These Kepler-51 planets are 10 times less dense than Saturn. They're roughly Jupiter-sized, but only a few Earth masses. If you could somehow stand on their surfaces, you'd barely feel any gravity. The atmospheres are enormously bloated with hydrogen and helium. Scientists initially thought these densities were measurement errors. They ran the observations again. The numbers held. These planets really are that puffy. The big question is why? What keeps these atmospheres so inflated? Several theories exist. Maybe the planets are young and still contracting from their formation. Maybe they have internal heat sources keeping the atmospheres warm and expanded. Maybe they're in a temporary phase before atmospheric loss brings them down to normal densities. Observations suggest they're actively losing atmosphere. The hydrogen and helium are escaping into space. These planets might look completely different in a few million years. We're seeing them during a brief puffy phase, but the Kepler-51 system has 3 superpuffs. If this is a temporary phase, what are the odds of catching all 3 planets in that phase simultaneously? Unless superpuffs are more common than we think, or unless the phase lasts longer than models predict. The system also raises questions about formation. How did 3 planets in the same system all develop these extreme characteristics? Did they form differently from normal planets? Or did they all experience similar evolution that led to puffiness? WASP-12 is dying. This planet has maybe 3 million years left. The ultra-hot Jupiter orbits so close to its star that tidal forces are literally ripping it apart. The star's gravity pulls the planet into an egg shape. Material from the planet's atmosphere streams toward the star in a steady flow. The planet is spiraling inward. Each orbit brings it slightly closer. The tidal forces grow stronger. The rate of atmospheric loss increases. Eventually, the planet will reach the Roche limit, where tidal forces overcome its self-gravity entirely. At that point, it will disintegrate completely. We're watching planetary death in progress. This planet won't survive astronomically long. 3 million years sounds like a long time. In cosmic terms, it's nothing. The dinosaurs went extinct 66 million years ago. This planet will be gone in less than 5% of that time span. The intense stellar radiation has heated the planet to over 2,500 degrees Celsius. That's hot enough to vaporize iron, aluminum, and titanium. The atmosphere glows in the visible spectrum from sheer heat. Observations show the planet is transferring mass to its star at an incredible rate. About 600 million tons per second flows from planet to star. The star is literally consuming its planet. This fate likely awaits many hot Jupiters. The closest ones will eventually succumb to tidal destruction. Their orbital decay might take millions or billions of years, but the end result is the same. The star wins. WASP-12b gives us a preview of that final chapter. We're witnessing something that happens frequently throughout the galaxy, but we rarely catch planets in this terminal phase because it happens relatively quickly. 2M1510AB orbits 2 brown dwarfs in a polar configuration. That sentence contains 3 separate oddities. First, brown dwarfs are failed stars. They're more massive than planets, but not massive enough to sustain hydrogen fusion. They glow from leftover heat, but don't truly shine. Only about 50 brown dwarf binaries are known. This planet orbits one of those rare pairs. Second, the planet orbits both brown dwarfs simultaneously. It's a circumbinary planet like Kepler-16b. Circumbinary orbits are uncommon because the gravitational dynamics are complex. The planet must navigate the combined gravitational fields of 2 objects. Third, the orbit is polar. The brown dwarfs orbit each other in one plane. The planet orbits perpendicular to that plane. It loops over the top of both brown dwarfs. Polar orbits around binary systems were predicted theoretically. Protoplanetary disks can be tilted or warped. If a disk is perpendicular to the binary's orbital plane, planets forming in that disk will have polar orbits. But 2M1510AB is the first confirmed example. The discovery proves polar circumbinary planets actually exist. They're not just theoretical possibilities. The orbital mechanics must be fascinating. The planet experiences constantly changing gravitational forces as the brown dwarfs orbit each other. Sometimes, both brown dwarfs pull in the same direction. Sometimes, they pull in opposite directions. The net gravitational force varies continuously. Somehow, the orbit remains stable despite this complexity. The planet found a configuration that works. It navigates the chaotic gravitational landscape without being ejected or colliding with either brown dwarf. This system provides insights into planetary migration and orbital evolution. Polar orbits don't form where planets form initially. The planet must have migrated from a different orbital configuration. Understanding how it reached this polar orbit tells us about the forces that reshape planetary systems. Rogue planets might outnumber stars. These worlds drift through interstellar space unbound to any star. Recent observations in the Orion Nebula detected hundreds of Jupiter-mass objects floating freely. They don't orbit stars. They travel through the galaxy on their own trajectories. About 80 of these objects are in binary pairs. 2 Jupiter-mass worlds orbit each other while both drift through space. Scientists call them jumbos. Jupiter-mass binary objects. How did they form? Several possibilities exist. Maybe they formed around stars and got ejected through gravitational interactions. Maybe they formed directly from cloud collapse like stars but didn't accumulate enough mass. Maybe they're the remnants of disrupted planetary systems. The binary nature of jumbos is particularly puzzling. If they formed around stars and got ejected, how did pairs of planets get ejected together while maintaining their mutual orbit? That requires very specific conditions. If they formed through direct collapse, why are so many in binaries? Binary star formation is common because collapsing clouds often fragment. But Jupiter mass objects are much smaller. The physics might be different. Detection of rogue planets is difficult. They don't emit much light. They don't pass in front of stars. We can only find them through gravitational microlensing or direct imaging in star-forming regions where they're still warm from formation. This means our census is incomplete. We've found hundreds. There might be billions in the Milky Way. Some estimates suggest rogue planets could outnumber stars by factors of hundreds or thousands. If true, the galaxy is full of dark worlds drifting silently between the stars, planets with no sunrise, no sunset, just the dim glow of distant stars and the blackness of space. Imagine one of those worlds up close, a rogue planet drifting through the Orion Nebula, no sunlight warming its surface, no star illuminating its clouds, just the perpetual night of interstellar space. The planet retains heat from its formation. Internal radioactive decay generates warmth. The core might still be molten. Convection could drive atmospheric circulation even without stellar input. But the surface would be frozen. Any water would be ice kilometers thick. Methane would be solid. Nitrogen would condense. The atmosphere, if one exists, would be thin and cold. Some rogue planets might have subsurface oceans heated by geothermal energy, like Europa's ocean beneath its ice shell, but without Jupiter's tidal heating. Just the planet's own internal heat. Could life exist in such environments? We don't know, but the sheer number of rogue planets means they could be common habitats. Now, let's shift gears completely, from worlds with no star to worlds with too much star. Kelt 9b represents the extreme upper limit of planetary temperatures. This ultra-hot Jupiter orbits so close to its star that its day side reaches 4,300 degrees Celsius. That's hotter than many stars. It's hotter than some red dwarfs. The planet receives so much radiation that molecules can't stay together. Hydrogen molecules split into individual atoms on the day side. The planet's atmosphere is atomic rather than molecular. When that atomic hydrogen flows to the night side, it cools enough to recombine into molecules. Then it flows back to the day side and gets torn apart again. This creates a continuous cycle of molecular dissociation and recombination. The Spitzer Space Telescope detected this process. The planet's year lasts 36 hours, orbital period shorter than Earth's day. It's tidally locked with one side permanently facing the star. The temperature difference between day and night drives supersonic winds. These winds redistribute heat around the planet, but they can't prevent the day side from reaching temperatures that vaporize metals. Iron and titanium exist as individual atoms in Kelt 9b's atmosphere, not bound in molecules, just floating freely. The planet also has magnesium and calcium in atomic form. Even some of the lighter rare earth elements have been detected. The star is massive and hot. It's an A-type star. These stars burn bright but brief. Kelt 9b won't survive forever. As the star ages and expands, it will eventually engulf the planet. But that's millions of years away. For now, Kelt 9b endures conditions more extreme than most planets could tolerate. Its atmosphere is probably being stripped away. The intense stellar radiation pushes atmospheric particles into space. The planet is evaporating slowly. Over time, it might lose its entire gaseous envelope. What would remain? Perhaps a rocky or metallic core, a hot remnant orbiting close to the star. Or maybe nothing. Maybe the entire planet will be consumed. TIC 241249530b has an orbit so eccentric it defies easy explanation. Most planets orbit in circles or near circles. Earth's orbit is nearly circular. Mars has slightly more eccentricity. But TIC 241249530b, its orbit is wildly elliptical. The eccentricity is 0.94. For comparison, comets have eccentric orbits. Halley's Comet has an eccentricity of 0.97. TIC 241249530b orbits like a comet, not a planet. At closest approach, it comes 10 times closer to its star than Mercury gets to our Sun. At its farthest point, it's as far out as Earth's orbit. The temperature swings must be extreme. Scorching heat at periastron. Moderate temperatures at apastron. The planet experiences seasons unlike anything in our solar system, not caused by axial tilt, but by orbital distance. What makes this orbit even stranger? The planet orbits backward. Most planets orbit in the same direction as their star's rotation. Prograde motion. TIC 241249530. B orbits retrograde against the star's rotation. This suggests a violent history. Planets don't naturally form in retrograde orbits. Something happened, perhaps gravitational interactions with another planet, maybe a close encounter with a passing star. The planet got scattered into this bizarre trajectory. Its orbit is consistent with ongoing tidal circularization. Over time, tidal forces from the star will gradually circularize the orbit. The planet will spiral inward. Eventually, it might become a hot Jupiter, a normal hot Jupiter with a circular orbit close to the star. But right now, it's caught in transition. We're witnessing planetary migration in action. The planet is on a journey from a distant, eccentric orbit to a close, circular one. This process takes millions of years. We're seeing a snapshot, a moment in the planet's evolution. Understanding TIC 241249530b helps us understand how hot Jupiters form. Many hot Jupiters probably went through similar phases, starting in distant orbits, getting scattered, then migrating inward. This planet shows us the pathway. WASP-12. B won't complete that journey. It's already too close, already doomed. This planet is spiraling toward destruction. It orbits its star in just 26 hours. The star is a yellow dwarf, similar to our Sun. But WASP-12b orbits far closer than any planet in our solar system. The proximity is killing it. Stellar gravity is tearing the planet apart. The planet is distorted into an egg shape. One side bulges toward the star. The other side stretches away. The planet is being pulled apart by tidal forces. It's also losing mass. The star's intense radiation heats the planet's atmosphere. Hot gas escapes into space. The planet is evaporating. Some of that material forms a disk around the star. The star is slowly consuming the planet. Models predict WASP-12. Pshar-Bar has about 3 million years left. That sounds like a long time. But in astronomical terms, it's nothing. The planet is living on borrowed time. What will remain after the planet is gone? Perhaps nothing. Maybe the entire planet will be consumed. Or maybe a small rocky core will survive, a hot, dense remnant orbiting close to the star. A planetary corpse, WASP-121b, shares similar characteristics. Another ultra-hot Jupiter tidally locked to its star. Dayside temperatures exceed 2,700 degrees Celsius, hot enough to vaporize iron, aluminum, and titanium. These metals exist as gases in the upper atmosphere. The temperature difference between day and night creates winds exceeding 16,000 kilometers per hour, faster than Earth's fastest hurricanes by orders of magnitude. The planet completes an orbit in 30 hours. It's so close to its star that it's also being distorted, stretched by tidal forces. The planet bulges toward the star. This distortion dissipates energy as heat, further heating the planet's interior. The combined effects of stellar radiation and tidal heating make WASP-121b1 of the hottest planets known. Its atmosphere has been studied extensively. Spectroscopy reveals water vapor, but this isn't liquid water. It's steam at temperatures that would vaporize steel. The planet also has unusual atmospheric chemistry. Observations detected gaseous titanium oxide and vanadium oxide. These compounds shouldn't be stable at such temperatures, yet they exist in WASP-121b's atmosphere. Perhaps they're constantly being replenished from the planet's interior. The planet might be so hot that rocks vaporize deep in the atmosphere. Material from the planet's mantle gets dredged up into the upper atmosphere. This creates exotic chemistry impossible in cooler environments. Let's examine the opposite extreme. LTT-9779b reflects 80% of incoming starlight, is the most reflective planet ever discovered. Earth reflects about 30%. Venus reflects about 75% due to its thick sulfuric acid clouds. LTT-9779b surpasses even Venus. The planet is Neptune-sized. It orbits very close to its star. Orbital period less than 1 day. This should make it a hot Neptune. And it is hot, but it shouldn't have an atmosphere. Planets this close to their stars typically lose their atmospheres. Stellar radiation strips away gas. Close-in Neptunes are rare. They occupy what astronomers call the hot Neptune desert. Most Neptune-sized planets orbit farther out. The few that orbit close in have lost their atmospheres and become rocky cores. LTT-9779b defies this pattern. It retained its atmosphere despite the harsh environment. How? The atmosphere contains metallic clouds, not water clouds or ammonia clouds. Clouds made of silicates and titanates, glass and titanium salts. These materials condense into droplets at the planet's temperature. They form reflective clouds that cover the entire planet. The metallic clouds reflect most incoming radiation. This prevents the atmosphere from heating up as much as it otherwise would. The clouds also have high mass. Heavy droplets aren't easily blown away by stellar wind. This allows the atmosphere to survive. The discovery of LTT-9779b was surprising. It shouldn't exist according to standard models, yet here it is, shining like a cosmic mirror. The planet teaches us that atmospheres can survive in unexpected places given the right conditions. Metallic clouds might be common on hot Neptunes. We just haven't observed many hot Neptunes because most lost their atmospheres. LTT-9779b 9779b might represent a rare survivor. Or perhaps our models need revision. Maybe hot Neptunes aren't as rare as we thought. Maybe we've been missing them because we weren't looking for the right signatures. This is a recurring theme in exoplanet science. Discovering something unexpected, revising our theories, discovering something else unexpected, revising again. Each discovery refines our understanding, but also reveals how much we don't know. Puffy, PSRB 1257+12 hosts, 3 planets. These aren't ordinary planets orbiting an ordinary star. They orbit a pulsar, a rapidly rotating neutron star. The pulsar formed in a supernova explosion. The star that preceded it collapsed, its core compressed into a sphere 15 kilometers across, unimaginably dense. A teaspoon of neutron star material would weigh billions of tons on Earth. The pulsar spins hundreds of times per second. It emits beams of radio waves. As it rotates, these beams sweep across space like a lighthouse. When the beam points toward Earth, we detect a pulse, hence the name pulsar. PSRB 1257 plus 12 spins every 6.2 milliseconds. That's incredibly fast. The planets were discovered in 1992. They were the first exoplanets ever confirmed. The discovery method was clever. Pulsars are extremely precise clocks. Their pulses arrive at regular intervals. If a planet orbits the pulsar, its gravity affects the pulsar's motion. The pulsar wobbles slightly. This causes tiny variations in pulse arrival times. By measuring these timing variations, astronomers detected 3 planets. PSR B 1257 plus 12. B is the innermost. It has less than twice Earth's mass, making it one of the lowest mass exoplanets known. PSR B 1257 plus 1, 2, C and D are larger, each several times Earth's mass. How did these planets form? Pulsars are created in supernova explosions. Supernovae are violent. They blow away most material in the stellar system. Any pre-existing planets would likely be destroyed or ejected. The planets around PSRB 1257 plus 12 probably formed after the supernova, from debris left behind. The explosion created a disk of material around the pulsar. Planets coalesced from this disk. Second-generation planet formation. These planets are unusual in another way. They orbit in a hostile environment. Pulsars emit intense radiation, X-rays, gamma rays, and charged particles. The planets are constantly bombarded. Any atmospheres would be stripped away quickly. The surfaces are probably barren and irradiated. Life on these worlds seems impossible. Yet the planets exist, defying the chaos that created them. Orbiting a dead star in the darkness. TOI 6894b challenges planet formation theory in a different way. Is a giant planet orbiting a tiny star. The star is a red dwarf, only 20% the size of the Sun. TOI 6894b is nearly as large as Jupiter. This combination shouldn't exist. According to the core accretion model of planet formation, planets grow by accumulating material from the protoplanetary disk. Giant planets need lots of material. Large disks form around large stars. Small stars have small disks. There isn't enough material to build giant planets. Yet TOI 6894b exists. A Jupiter-sized planet around a star 1/5 the Sun's size. The planet has about half Jupiter's mass. It's inflated due to heat from its star, but it's still a giant planet. The discovery was announced in 2025. Astronomers are puzzled. How did this planet form? One possibility is the core accretion model needs refinement. Maybe small stars can have larger disks than we thought. Or maybe the planet formed differently, perhaps through gravitational instability. If the disk was massive enough, it could collapse directly into a planet without going through the core accretion process. But gravitational instability usually requires specific conditions we didn't think existed around red dwarfs. LHS 3154b is similar. Another impossible planet around a tiny star. This planet is 13 times Earth's mass. Its star is 9 times less massive than the Sun. The mass ratio is extreme. The planet is too large relative to its star. Our best theories can't explain it. Future studies might reveal how these planets formed. Or maybe they'll just deepen the mystery. TO-I689, 4b, and LHS 3154b aren't alone. As we discover more planets around low-mass stars, we might find that giant planets are more common than expected. This would force a major revision of planet formation theory. Or perhaps these are genuinely rare exceptions, flukes of unusual circumstances. Either way, they expand our understanding of what's possible. Every impossible planet teaches us something. It shows us that nature is more creative than our theories, that the universe finds ways we haven't imagined, that reality is always stranger than our models predict. 2. M1510 AB. B takes weirdness to another level. The planet orbits not one star, but 2. That's not unheard of. Kepler 16b does the same thing. But 2 M1510 ABB stars aren't normal stars. They're brown dwarfs, failed stars that never quite ignited nuclear fusion. Only one other circumbinary planet has been found orbiting a brown dwarf pair. That alone makes it rare. But the orbit itself is what makes astronomers stop and stare. Most planets orbit in roughly the same plane as their stars, like a vinyl record spinning flat. This is true throughout our solar system. All the planets circle the Sun in approximately the same flat disk. It's how planetary systems form, from a flat protoplanetary disk of gas and dust. 2 M1510 AB. B doesn't follow this rule. It orbits at 90 degrees to the plane of its brown dwarfs. Imagine those brown dwarfs spinning around each other horizontally. Now imagine the planet looping over the top and under the bottom, like a Ferris wheel going up and down while they spin sideways. That's a polar orbit. It's the first planet ever found in a polar orbit around a binary system. How did it get there? Planets don't form in polar orbits. They form in the disk, in the same plane as everything else. Something must have knocked this planet out of alignment. Maybe gravitational interactions with another object. Maybe a close encounter with a passing star. We don't know yet. The discovery tells us that planetary orbits can be far more chaotic than we imagined. That planets can migrate not just inward or outward, but up and down through their systems. That binary systems can sculpt planetary orbits in unexpected ways. WASP 107 B reveals another kind of strangeness, not in its orbit, but in its atmosphere. The planet is Jupiter-sized, but only 1/10 Jupiter's mass. A superpuff. Its atmosphere is extremely inflated, low density, low gravity. This makes it ideal for studying atmospheric composition. Light passes through more atmosphere, making spectral features easier to detect. In 2023, astronomers found something unusual. The planet's atmosphere is asymmetric. The eastern and western edges look different. Temperature differences, composition differences. One side is not like the other. This shouldn't happen on a tidally locked planet. Tidally locked worlds have one side always facing the star, the other side always facing away. You'd expect east and west to be fairly similar. North and south might differ due to atmospheric circulation, but east and west should be symmetric. WASP 107b breaks this expectation. The asymmetry suggests complex atmospheric dynamics, maybe powerful jet streams, maybe unusual wind patterns, maybe localized weather systems unlike anything we've seen. The planet is teaching us that even our best models of atmospheric circulation are incomplete. We don't have anything like WASP 107b in our solar system. No comparison point. Every measurement is a surprise. GJ1132b tells a story of transformation. The planet orbits a red dwarf star. It's slightly larger than Earth, rocky, not gaseous. For a long time, astronomers thought it was just another rocky world, tidally locked, probably airless, not particularly interesting. Then they looked closer. The planet has an atmosphere. That's not shocking. But this atmosphere is unusual. It's thick, rich in hydrogen. Hydrogen atmospheres are typically found on gas giants or mini Neptunes, not rocky planets. Here's where it gets interesting. Astronomers think GJ1132b was once a mini Neptune, a small gas giant with a thick hydrogen envelope, but its star is active. Red dwarfs often are. Stellar flares, intense radiation. This radiation stripped away the planet's original atmosphere. The hydrogen and helium were blown off into space. The planet became a bare rock. But the story didn't end there. Underneath the lost atmosphere was a rocky core. That core had geological activity, volcanism, outgassing. Over millions of years, volcanic eruptions released gases from the planet's interior: carbon dioxide, methane, hydrogen sulfide. A new atmosphere formed, a secondary atmosphere, born from the planet itself. This is the first planet where we've seen evidence of a secondary atmosphere forming after the original one was lost. It suggests that planets can be more resilient than we thought, that atmospheric loss isn't always permanent, that volcanic activity can give planets a second chance. If this can happen on GJ1132b, it might happen elsewhere, on other rocky worlds around active stars, maybe even on some of the rocky planets in the TRAPPIST-1 system. This opens new possibilities for atmospheric evolution and habitability. HR 5183b has an orbit so extreme it was nicknamed the Wrecking Ball. The planet is 3 times Jupiter's mass, a super Jupiter. It takes 74 years to complete one orbit. That's a long year. But the orbit itself is what stands out. Most planetary orbits are roughly circular. Earth's orbit is nearly a perfect circle. Even Jupiter's orbit is pretty round. But HR 5183b's orbit is stretched into a long ellipse, an eccentricity of 0.9, almost as eccentric as an orbit can be without the planet escaping entirely. What does this mean? The planet spends most of its time far from its star, loitering in the cold outer reaches of the system. Then it plunges inward, swinging close to the star before hurtling back out, like a comet but planetary-sized. At its closest approach, it comes within about the distance of Mercury from its star. At its farthest, it travels beyond Jupiter's equivalent distance. That's an enormous range. If there were other planets in this system, HR 5183b would wreak havoc on them. Its gravity would perturb their orbits, maybe eject them entirely. It's possible this planet is the reason there aren't other planets visible in the system. It might have thrown them out long ago. How did HR 5183b get such an eccentric orbit? Probably through gravitational interactions. Maybe with another planet that was later ejected. Maybe with a passing star. Stellar encounters can scatter planets like billiard balls. The discovery was made using the radial velocity method, watching the star wobble over many years, detecting the subtle gravitational tug of the planet. It takes patience to find planets with such long orbits. You have to watch for decades. HR 5183b reminds us that planetary systems are dynamic. They evolve over time. Planets migrate, orbits change. Systems that look stable now might have been chaotic in the past. WASP 12b is a planet on death row. The planet orbits its star once every 26 hours. That's close. Really close. So close that the star's gravity is tearing it apart. The planet is distorted into an egg shape, stretched by tidal forces. Its atmosphere is being stripped away. Material from the planet is spiraling into the star. WASP 12b is doomed. In about 3 million years, it will be completely consumed. We're witnessing planetary death in real time. The planet is hot, over 4,000 degrees Fahrenheit, tidally locked. One side always faces the star. That side is even hotter, hot enough to vaporize metals. The planet's atmosphere is filled with exotic compounds, titanium oxide, vanadium oxide. These molecules condense on the cooler night side, forming clouds of metal oxides. But the most striking thing is the mass loss. The planet is losing material at an incredible rate, 100 billion tons per year. That sounds like a lot. But remember, the planet is massive. It'll take millions of years to completely evaporate. But the process is irreversible. WASP-12b is part of a class of planets called ultra-hot Jupiters. These are gas giants that orbit so close to their stars, they're slowly being destroyed. They represent the endgame of planetary migration, planets that spiraled inward and got too close. Why study a dying planet? Because it teaches us about planetary interiors. As the outer layers are stripped away, we get to see what's underneath. Like an archaeological dig, but for planets. We can study the composition of deeper layers, understand how gas giants are structured. WASP-12b also teaches us about planetary migration, how planets move inward over time, the mechanisms that drive migration, and the ultimate fate of planets that get too close to their stars. Not all planets die this way. Some migrate inward and settle into stable orbits, hot Jupiters that will survive for billions of years. But some, like WASP-12b, cross a threshold. They get close enough that tidal forces become destructive, and there's no going back. LTT 9779b is the opposite of TRIS-2b. Instead of absorbing light, it reflects it. LTT 9779b reflects 80% of the light that hits it, the highest albedo of any exoplanet known. It's like a giant mirror in space. How? The planet's atmosphere is filled with metallic clouds, silicate clouds, glass clouds, titanate clouds. These clouds are highly reflective. They bounce light back into space like a polished surface. The planet shouldn't exist. It orbits its star in just 19 hours. It's in a region called the hot Neptune Desert, a zone where Neptune-sized planets are rare. They usually don't survive. The stellar radiation is too intense. It strips away their atmospheres. But LTT 9779b has survived. Its metallic clouds might be the key. The metals in the atmosphere are heavy, too heavy for the stellar wind to easily blow away. The clouds act as a shield, protecting the planet from atmospheric loss. The planet is also incredibly hot, around 3,000 degrees Fahrenheit, hot enough to vaporize most metals. But the pressure in the atmosphere is so high that metals can condense into clouds. It's like a pressure cooker in space. LTT 9779b is teaching us about atmospheric chemistry under extreme conditions, how metals behave at high temperatures and pressures, how planets can survive in hostile environments, how reflectivity can protect an atmosphere from being stripped away. The planet is also beautiful. If you could see it up close, it would shine brilliantly, a dazzling jewel in the darkness. PSRJ 2322-2650b is one of the newest discoveries, announced in 2025. And it's baffling. The planet orbits a pulsar, like the planets around PSRB 1257 plus 12. But this one is different. It's Jupiter mass. The pulsar is tiny, a neutron star only about 20 kilometers across. The planet completes an orbit in less than 8 hours. The planet's atmosphere is bizarre, dominated by helium and carbon instead of hydrogen, shrouded in dark, soot-like clouds. The carbon in the atmosphere might be compressed into diamonds deep inside the planet. A diamond planet orbiting a dead star. The gravity of the pulsar is so strong it distorts the planet's shape. The planet is stretched into a lemon shape, elongated along the axis, pointing toward the pulsar. Tidal forces are extreme. No theory predicted this planet could exist. Pulsars are created in supernova explosions. Those explosions should destroy any nearby planets. Yet here's a Jupiter mass planet orbiting one. How did it form? Maybe it's a second-generation planet, formed from the debris of the supernova. But that doesn't explain its unusual composition, or its incredibly short orbit. Maybe it's a captured planet, a rogue world that wandered too close to the pulsar and got trapped. But capturing a planet is difficult. The odds are low. Maybe it's something else entirely, a new type of object we don't have a name for yet, an intermediate between a planet and a failed star. PSRJ 2322-2650b is forcing astronomers to rethink what's possible, to reconsider the boundaries between planets, brown dwarfs, and stellar remnants, to ask whether our categories are too rigid. Every new discovery expands the definition of what a planet can be. Every strange world challenges our assumptions. Every impossible planet teaches us that nature is more creative than our theories. We've found planets made of diamond, planets darker than coal, planets where it rains glass or iron, planets orbiting two stars, planets orbiting dead stars, planets with no stars at all, planets with polar orbits, planets with asymmetric atmospheres, planets losing their atmospheres and growing new ones, planets being torn apart by their stars, planets that shine like mirrors, and we've barely scratched the surface. Out of the billions of planets in our galaxy, we've found only a few thousand. The weird ones stand out because they're easy to detect or particularly unusual. But there are likely countless other bizarre worlds waiting to be discovered. Worlds with conditions we can't imagine. Atmospheres made of compounds we've never considered. Orbits that defy our current understanding. The universe is stranger than we thought, and stranger than we can think. These discoveries force us to reconsider everything we thought we knew about planetary systems. TOI 6894b shouldn't exist. The planet was announced in June 2025, and it immediately became a problem. It orbits a red dwarf star, a tiny star only about 20% the size of our Sun. But the planet is almost as big as Jupiter. That combination violates our theories. According to current models of planet formation, small stars can't have large planets. The protoplanetary disk around a small star doesn't contain enough material. There isn't enough gas and dust to build a gas giant, yet there it is, massive, orbiting a star that shouldn't be able to create it. Another planet called LHS 3154b presents the same puzzle. Discovered in 2023, about 13 times Earth's mass, its star is 9 times less massive than our Sun. The planet is far too large for its star. Researchers called it impossible. These discoveries aren't just anomalies, they're challenges. They suggest our understanding of planet formation has significant gaps. Maybe small stars can accumulate more material than we thought. Maybe planet formation is more efficient under certain conditions. Maybe planets can migrate from farther out in the system where more material exists. Or maybe we're missing something fundamental about how planetary systems assemble. TOI 6894b and LHS 3154b are forcing astronomers to revisit their models, to test new scenarios, to consider mechanisms they'd previously dismissed. 2M1510AB. B takes weirdness in a different direction. It's a circumbinary planet, meaning orbits 2 stars. That's rare, but not unique. We've found about 16 circumbinary systems, but 2M1510AB. B orbits 2 brown dwarfs, failed stars that never ignited fusion. Only one other system like it has been found. What makes this planet truly bizarre is its orbit. It's on a polar orbit. At 90 degrees to the plane the brown dwarfs orbit in. The planet loops over the top of the brown dwarfs, like a ball circling a spinning wheel. It's the first polar circumbinary planet ever detected. Astronomers had suspected such orbits might exist. They'd found protoplanetary disks at polar angles. But finding an actual planet in such an orbit is extraordinary. How did it get there? Planets form in the disk of material surrounding young stars. That disk is usually flat. Planets should orbit in the same plane as the disk. A polar orbit suggests something dramatic happened. Some gravitational interaction threw the planet out of the disk's plane. Maybe another planet. Maybe a passing star. Or maybe the planet formed differently, in a disk that was already tilted. 2M1510AB BB is teaching us about planetary migration, about gravitational dynamics in multi-body systems, about how orbits can evolve over millions of years. WASP 107b reveals another surprising feature: atmospheric asymmetry. The planet is the size of Jupiter, but only 1/10 its mass. It's a super puff, incredibly low density, an inflated atmosphere. When astronomers studied the planet's atmosphere, they found something unexpected. The east and west sides of the planet are different. There's a significant asymmetry in atmospheric composition and temperature. We don't have anything like WASP 107b in our solar system. Nothing this puffy, nothing this light. The asymmetry suggests complex atmospheric dynamics. Winds don't circulate evenly. Chemical processes differ between hemispheres. Maybe the planet's rotation affects how heat distributes. Maybe there are localized weather systems, permanent storms or high-pressure zones. WASP 107b is giving scientists unprecedented insight into gas giant atmospheres, how they behave under low gravity, how chemicals mix and react, how energy moves through inflated atmospheres. GJ1132 presents a different kind of transformation. It's a rocky world slightly larger than Earth, orbiting a red dwarf star. Scientists believe it started as a mini Neptune, a small gas giant with a thick hydrogen atmosphere. But the star's radiation stripped that atmosphere away. The planet lost its original atmosphere completely. Now here's the fascinating part. It grew a new one. Volcanic activity released gases from the planet's interior. Carbon dioxide, nitrogen, maybe methane. A secondary atmosphere formed, not from primordial gases, but from geological processes. This is the first planet where we've observed such a transformation. It suggests planets can have multiple atmospheric regimes over their lifetimes. They can lose atmospheres and regrow them, evolve from one type of world to another. GJ1132b is showing us that planetary evolution is more complex than we imagined. Atmospheres aren't static. They respond to internal and external forces. Geology and astronomy interact in ways we're only beginning to understand. HR5183b features one of the most eccentric orbits ever discovered. It's a super Jupiter, 3 times more massive than our largest planet. It takes 74 years to complete one orbit. But that orbit is extremely elongated, egg-shaped. The planet spends most of its time far from its star, loitering in the outer reaches of the system. Then it plunges inward, slingshotting past its star at high speed. It swings from distances beyond Earth's orbit to regions closer than Mercury. The temperature swings are extreme, from frozen to scorching and back again. How does a planet end up in such an orbit? Gravitational interactions. Probably with another massive planet. 2 planets in the same system can gravitationally scatter each other. One gets flung outward or ejected entirely. The other ends up on an eccentric orbit. HR 5183be might be the sole survivor of a chaotic early history. Its companion planet may have been ejected, lost to interstellar space. Or maybe the companion is still out there, in the distant outer system, too far and too faint to detect yet. HR 5183b is teaching us about planetary system dynamics, about gravitational scattering, about how planetary systems can be violent and unstable. Our solar system is calm now. Orbits are mostly circular and stable. But it wasn't always that way. Early in its history, planets migrated, orbits shifted. Jupiter and Saturn may have moved significantly. Neptune might have formed closer to the Sun. HR 5183b is showing us what planetary chaos looks like, what happens when massive worlds interact gravitationally, when systems haven't settled into stability yet. Every one of these bizarre planets challenges our assumptions. We thought we understood how planets form, where they form, what they're made of. We thought gas giants only existed far from their stars. We thought planets needed solid surfaces or thick atmospheres, but not both extremes. We thought planetary systems resembled ours, stable, predictable. We were wrong. The universe is far more inventive than our theories predicted. Planets can form in ways we didn't expect, in places that seem impossible. They can migrate, transform, lose atmospheres and grow new ones. They can orbit pulsars, rogue through space alone, circle two stars or failed stars. They can have polar orbits, asymmetric atmospheres, orbits that defy logic. Each discovery expands what we know is possible, and each discovery raises new questions. How do these planets form? How do they survive in such extreme environments? What other kinds of bizarre worlds are out there waiting to be found? The techniques we use to find exoplanets have limitations. We find planets that are large, or close to their stars, or that transit in front of their stars from our perspective. Small planets far from their stars are nearly impossible to detect with current technology. Rocky planets around dim stars are hard to find. Planets in wide orbits take decades to complete one orbit. We haven't observed them long enough to see patterns. This means we're seeing a biased sample. The weird planets we've found are the ones we can find. There are likely countless others, even stranger, even more extreme. Planets with conditions we haven't imagined yet, atmospheres made of compounds we've never considered, surfaces with geology we can't predict. The James Webb Space Telescope is revealing new details about exoplanet atmospheres. It can detect molecules, identify chemicals, measure temperatures across different regions. JWST is finding water vapor, carbon dioxide, methane, sulfur compounds. It's mapping temperature gradients, tracking cloud formations, observing weather patterns. Future telescopes will push further. The Extremely Large Telescope, the Habitable Worlds Observatory. They'll find smaller planets, study atmospheres in greater detail. They'll search for biosignatures, signs of life on distant worlds. But for now, the bizarre planets we've discovered are enough to keep scientists busy for years, trying to explain them, model them, understand them. Each planet is a laboratory, a natural experiment in planetary physics. We can't visit them, can't send probes. We can only observe from light years away, analyze the light that reaches us, infer what we can. But that's enough, because every photon carries information. Every spectrum reveals composition. Every transit tells us about size and orbit. The universe is speaking in wavelengths of light, in the wobble of stars, in the dimming of distant suns. We just have to listen carefully. And what the universe is telling us is this: planets are more diverse than we ever imagined. The rules we thought governed planetary systems are more flexible than we believed. Nature finds ways, loopholes in our theories, configurations we didn't predict. The bizarre planets aren't exceptions. They're reminders that our theories are incomplete, that the universe has been experimenting with planetary formation for billions of years, And it's come up with solutions we're only beginning to discover. The darkest planet, the brightest planet, the hottest, the puffiest, planets that rain iron or glass, planets made of diamond or sapphire, planets orbiting dead stars, planets orbiting no stars at all, planets with polar orbits, asymmetric atmospheres, impossible sizes. Each one expands the definition of what a planet can be. Each one forces us to think bigger, to imagine more possibilities, to accept that the cosmos is stranger than our limited experience suggested. We grew up on one planet, in one solar system. We thought that was normal, that other systems would resemble ours. But Earth isn't normal. It's one possibility among countless others. Our solar system isn't a template. It's an example, and the bizarre exoplanets we're discovering prove that the universe has no shortage of creativity. Every civilization that has ever looked up at the stars has asked the same question. Are we alone? We still don't have the answer. But the bizarre exoplanets we've discovered have reframed the question entirely. Finding life on another world would be the most profound discovery in human history. It would change philosophy, religion, science, our entire understanding of our place in the cosmos. But here's what the bizarre planets are teaching us. Life might not look anything like we expect. We've been searching for Earth-like planets, worlds with liquid water, moderate temperatures, stable atmospheres, orbits in the habitable zone. But that's based on a sample size of 1. Life on Earth. What if life doesn't need Earth-like conditions? What if biology is far more flexible than we imagine? The extremophiles on Earth give us hints. Bacteria thriving in boiling hot springs, microbes living kilometers beneath the ocean floor, organisms surviving in acid lakes, radiation-resistant bacteria that can withstand doses that would kill anything else. If Earth can support such diversity of life in extreme environments, what might thrive on worlds we consider hostile? Could there be life in the upper atmospheres of hot Jupiters? Floating organisms drifting through clouds of hydrogen and helium? We don't know, but we can't rule it out. The super puff planets with their enormous atmospheres might harbor aerial ecosystems we've never imagined. The tidally locked planets with permanent day and night sides could have life adapted to extreme temperature gradients. The rogue planets drifting through interstellar space might have subsurface oceans kept liquid by internal heat. Every bizarre planet expands the possible habitats for life. They force us to think beyond our terrestrial prejudices, to consider biochemistries based on different solvents, metabolisms using different energy sources, life forms adapted to conditions we'd consider impossible. The James Webb Space Telescope is beginning this search. It's analyzing exoplanet atmospheres, looking for biosignatures, gases that might indicate biological activity, oxygen, methane, phosphine, combinations of gases that shouldn't exist together unless something is producing them. But even that assumes life produces similar waste products to Earth life. What if alien biology creates completely different byproducts? What if the signs of life are chemicals we haven't thought to look for? The bizarre planets remind us that nature is more creative than our theories, that the universe finds solutions we don't predict, that the rules are more flexible than we believed. Consider PSRJ 2322-2650. orbiting its pulsar. Nobody thought planets could survive the violent supernova that creates a neutron star. Yet there it is. If planets can survive that, what else is possible? Or TOI-6894b, the Jupiter-sized planet orbiting a red dwarf star. It shouldn't exist, according to our formation models. But it does. Our models were incomplete. Every impossible planet forces a revision of our theories. Every bizarre world expands the realm of the possible. And with each expansion, the potential habitats for life increase. The search for life beyond Earth isn't just about finding Earth 2.0. It's about recognizing that life might thrive in environments we've overlooked. That biology might be far more adaptable than we give it credit for. The next generation of telescopes will push these searches further. The Extremely Large Telescope, the Habitable Worlds Observatory. They'll study smaller planets, analyze atmospheres in unprecedented detail, search for definitive signs of life. But even without finding life, the bizarre exoplanets have taught us something crucial. The universe is far stranger than we imagined, far more diverse, far more creative in the solutions it finds. We're still in the early stages of exoplanet exploration. We've discovered thousands, but there are hundreds of billions of stars in the Milky Way alone. Most of them probably have planets. The sample we've found is tiny, and already in that tiny sample, we've found worlds that defy explanation, planets that challenge our theories, systems that shouldn't exist, atmospheres that violate our predictions. What will we find when we've surveyed a larger fraction of the galaxy? When our telescopes become more sensitive? When our detection methods improve? The truly bizarre planets might be ones we haven't found yet. Worlds so strange we lack the conceptual framework to even predict them. There could be planets with magnetic fields so strong they warp the structure of atoms, worlds where exotic states of matter exist on the surface, planets with atmospheres so dense the boundary between gas and liquid disappears. We don't know, but the universe has surprised us at every turn. The iron rain of WASP 76b seemed impossible before we found it. The glass rain of HD 189733b, the darkness of TAR-ES 2b, the puffiness of the cotton candy planets. Each discovery expanded what we thought was possible. Future discoveries will do the same. They'll challenge our assumptions, force us to revise our theories, expand the boundaries of planetary science. And with each expansion, we'll understand more about how planetary systems form, evolve, and endure. The bizarre planets are also teaching us about our own solar system, about how unique or typical it might be, about the processes that shaped the worlds we grew up studying. Jupiter might seem like a gentle giant compared to hot Jupiters, but it played a crucial role in Earth's history. Its gravity deflected comets and asteroids, protected the inner solar system. Without Jupiter, Earth might have been bombarded far more frequently. Complex life might never have evolved. Saturn's rings seemed unique until we found ring systems around exoplanets. Mars seemed like the obvious place to search for life until we discovered moons with subsurface oceans. Europa, Enceladus, Titan. Each new discovery reframes our perspective. The bizarre exoplanets are mirrors. They reflect back insights about our own cosmic neighborhood. They help us understand what makes Earth special and what makes it ordinary. Earth sits in the habitable zone, has liquid water, a magnetic field, a stable climate, an atmosphere that protects but doesn't crush, conditions that allowed life to arise and evolve over billions of years. That combination might be rare, or it might be common. We don't know yet, but the diversity of exoplanets suggests that Earth-like worlds exist somewhere. Statistically, they must. The question isn't whether they exist, it's how common they are, and whether any of them host life. The bizarre planets also raise questions about the future, about what happens to planetary systems over deep time. WASP-12b is being destroyed by its star. In a few million years, it'll be gone. What happens then? Does the star engulf other planets? Does the system stabilize? We're watching planetary death in real time. The rogue planets tell a different story. Ejected from their systems, wandering through the void. Do they remain frozen forever? Or could they eventually be captured by another star? Could a planet have multiple stellar parents over its lifetime? These questions matter because they tell us about the ultimate fate of all planetary systems, including our own. In about 5 billion years, the Sun will expand into a red giant. It'll engulf Mercury and Venus, possibly Earth. The outer planets might survive, but the solar system we know will be unrecognizable. Will there be bizarre remnant planets orbiting the Sun's white dwarf core? Will some planets be ejected to become rogues? The answers lie in studying systems at different stages of evolution, watching how planets respond to stellar changes, observing the death throes of other worlds. The bizarre exoplanets are time machines, windows into the past and future. Young systems show us how planets form. Middle-aged systems show us stable evolution. Dying systems show us the endgame. Each one is a snapshot of a different moment in the cosmic story. And that story is still being written. New planets are being discovered constantly. New techniques are being developed. New telescopes are being built. The field of exoplanet science is accelerating. In the next decade, we'll find thousands more planets. We'll characterize hundreds of atmospheres. We'll detect biosignatures, or we won't. Either answer is profound. Either answer changes everything. If we find life, we'll know we're not alone. That biology isn't unique to Earth, that the universe is teeming with living worlds. The implications would reshape civilization. If we don't find life, we'll know it's rare, that Earth is special, that we carry a profound responsibility as possibly the only conscious observers in our corner of the galaxy. That would be equally significant, but regardless of whether we find life, the bizarre exoplanets have already taught us the most important lesson. The universe is stranger, more diverse, more creative than our limited experience suggested. Nature finds ways, configurations we didn't predict, solutions we didn't imagine. Every bizarre planet is a reminder that we're still at the beginning, that we're cosmic infants, just learning to see beyond our nursery, that the galaxy holds secrets we haven't begun to uncover. The darkest planet exists. The brightest planet exists. Planets rain iron and glass. Planets orbit dead stars and no stars. Planets form where they shouldn't, survive what they shouldn't, exist in configurations that defy our models. And those are just the ones we've found, the ones we can detect with current technology, the ones that happen to be large enough, close enough, bright enough for us to see. Somewhere out there are planets even stranger, worlds that would redefine bizarre, systems that would shatter our remaining assumptions. And we're going to find them, because humanity is just getting started with this exploration. We're building better tools, developing better techniques, training new generations of astronomers who will push further into the unknown. The bizarre exoplanets aren't anomalies. They're the universe showing us its true nature, diverse beyond comprehension, creative beyond prediction, stranger than we can imagine. And that's the real lesson. Not that these specific planets exist, but that the cosmos refuses to be constrained by our expectations, that nature is always more inventive than our theories, that the universe will always surprise us if we're willing to look. We stand at a threshold, looking out at a galaxy we're only beginning to understand. 6,000 confirmed exoplanets. That sounds like a lot, until you remember there are hundreds of billions of stars in the Milky Way. Most of them probably have planets. We've sampled a fraction of what's out there, and already the universe has shattered every assumption we made. We thought planetary systems would resemble ours, orderly, predictable, rocky planets near the star, gas giants farther out, everything arranged in neat circular orbits. The universe laughed at that assumption. It gave us hot Jupiters orbiting closer than Mercury, superpuffs with the density of cotton candy, planets darker than coal and brighter than mirrors, worlds where it rains molten iron or glass shards traveling at supersonic speeds. We thought planets needed stars. The universe showed us rogues drifting alone through the void, hundreds of them, possibly billions, some traveling in pairs, tumbling through the darkness together with no sun to warm them. We thought planets couldn't survive supernova. The universe proved us wrong, showed us worlds orbiting pulsars, second-generation planets born from stellar death. We thought small stars couldn't make giant planets. TOI 6, 894b, and LHS 3154b exist anyway. Impossible planets that force us to rewrite our formation theories. Every discovery reveals how little we actually know, how many assumptions we made based on a sample size of 1, how limited our perspective was when we thought Earth represented normal. Earth isn't normal. It's one possibility among countless others. Our solar system isn't a template. It's an example. One configuration among infinite variations. The bizarre planets aren't exceptions. They're not outliers or flukes. They're the universe demonstrating its range, showing us the full spectrum of what's possible. And we're only seeing the ones we can detect, the large ones, the close ones, the ones that happen to pass in front of their stars from our viewing angle. Small rocky worlds in distant orbits remain invisible. Planets around dim red dwarfs hide in the glare. Worlds in wide orbits take decades to complete one revolution. We haven't watched long enough to see the pattern. The truly bizarre planets might still be hidden, waiting for better telescopes, more sensitive instruments, new detection methods we haven't invented yet. What will we find when we can see smaller planets, when we can study worlds orbiting farther from their stars, when our atmospheric analysis becomes detailed enough to map weather systems and chemical compositions in real time? We'll find more impossibilities, more violations of our theories, more configurations we didn't predict, because that's what the universe does. It finds solutions we never considered, loopholes in physical laws we thought were rigid. The James Webb Space Telescope is giving us unprecedented views of exoplanet atmospheres, detecting molecules we couldn't see before, mapping temperature variations across planetary surfaces, finding chemicals that shouldn't exist together, observing weather patterns on worlds dozens of light years away. Future telescopes will push further. The extremely large telescope will study smaller planets in greater detail. The Habitable Worlds Observatory will search specifically for signs of life, for biosignatures in atmospheric chemistry, for oxygen and methane and phosphine in combinations that suggest biology. Maybe we'll find life. Maybe we won't. Either answer is profound. If we find it, we'll know we're not alone, that Earth isn't unique, that biology emerges wherever conditions allow, that the universe is full of living worlds. Some of them might be bizarre beyond imagination. Life adapted to environments we'd consider hostile. Organisms floating in the clouds of hot Jupiters. Microbes in subsurface oceans on rogue planets. Ecosystems thriving on worlds with no sun. If we don't find life, we'll know it's rare, that Earth is special, that we carry a responsibility as possibly the only conscious observers in our region of space. That would be equally significant, equally humbling, but the search itself teaches us something regardless of the outcome. It forces us to think bigger, to imagine possibilities beyond our terrestrial experience, to accept that nature is more creative than our limited perspective suggested. Every bizarre planet expands the boundaries of what we consider possible. Each discovery challenges our assumptions, forces revisions to our theories, opens new questions we didn't know to ask. The iron rain of WASP 76b, the glass storms of HD 189733b, the pitch blackness of TRES 2b, the mirror shine of LTT 9779b, the diamond composition of 55 Cancri E, the cotton candy density of Kepler 51's worlds, the pulsar planets, the polar orbits, the impossible giants around tiny stars. Each one seemed impossible until we found it. Each one violated some rule we thought was fundamental. And each one forced us to acknowledge that our rules were incomplete. The universe doesn't care about our models. It builds whatever physics allows, and physics allows far more than we imagined. Planets can form in ways we didn't predict, survive conditions we thought were lethal, exist in configurations we thought were impossible. The cosmos has been experimenting with planetary systems for billions of years, trying every possible variation, testing every configuration, finding solutions we're only beginning to discover. We're cosmic infants, just learning to see beyond our own star system, just beginning to understand the diversity that exists out there. We've been doing this for barely 30 years. The first confirmed exoplanet was found in 1992. 3 decades. That's nothing on cosmic timescales. And in those 3 decades, we've discovered over 6,000 worlds, each one teaching us something new, each one expanding our understanding of what planets can be. Imagine what we'll know in another 30 years, in a century, in 1,000 years, assuming we survive long enough to keep exploring, keep building telescopes, keep analyzing data, keep asking questions. The bizarre exoplanets are invitations, doorways into a universe far stranger than we suspected, windows into processes we don't fully understand. laboratories for testing physics under extreme conditions we can't reproduce on Earth. They're also mirrors, reflecting back insights about our own solar system, about how typical or unusual Earth might be, about the processes that shape the worlds we grew up studying, about what makes life possible or impossible. Every discovery reframes our perspective, changes how we see our place in the cosmos, challenges what we thought we knew about planetary science, astronomy, physics, chemistry, biology. The universe is speaking in wavelengths of light, in the wobble of distant stars, in the dimming of suns as planets pass in front of them, in the gravitational lensing of background galaxies, in the radio pulses from spinning neutron stars. We're learning to listen, building better instruments to hear those cosmic whispers, developing better techniques to extract information from faint signals, training new generations of astronomers to push further into the unknown. And what the universe is telling us is this: it's bigger than we thought, stranger than we imagined, more diverse than our theories predicted, more creative than our models allowed. The bizarre exoplanets aren't anomalies. They're the norm. Earth is the oddity. Our solar system is the exception. Stable, orderly, predictable. That's unusual. Most planetary systems are chaotic, dynamic, constantly evolving. Planets migrate, orbits shift, worlds collide or get ejected. Systems that look stable now were violent in their youth, and some remain violent. HR 5183b with its wrecking ball orbit, TIC 241249530b with its extreme eccentricity. These are systems still in flux, still settling, still finding equilibrium. Our solar system is calm because it's old. It had billions of years to settle down, to eject the troublemakers, to circularize orbits, to reach a stable configuration. But it wasn't always this way. Early in its history, planets moved. Jupiter and Saturn migrated. Neptune shifted outward. Uranus got knocked on its side. The late heavy bombardment scarred the inner planets. We're past that violent phase now, but other systems are still living through it, and we're watching, learning from their chaos, understanding the processes that shape planetary systems over deep time. The bizarre planets are time machines, windows into different stages of planetary evolution. Young systems show us formation in action. Middle-aged systems show us stability and maturation. Dying systems show us the endgame. WASP 12b, spiraling into its star. Pulsar planets orbiting stellar corpses. Rogue planets cast into the void. Each stage teaches us something about where we came from, where we're going, what's possible in between. In about 5 billion years, our sun will expand, become a red giant, swallow Mercury and Venus, possibly Earth. The solar system will transform into something unrecognizable. The outer planets might survive, but they'll be different, heated by the bloated sun, their ices melting, their moons transforming. And eventually, the sun will shed its outer layers, become a white dwarf. The remaining planets will orbit a stellar corpse, like the pulsar planets we've discovered. Our future written in their present, but that's 5 billion years away. For now, we're here, conscious observers on a small rocky planet, looking out at the cosmos with increasingly powerful eyes, discovering worlds that challenge everything we thought we knew, and learning to accept that the universe is under no obligation to make sense to us. It doesn't care about our theories, our models, our assumptions. It simply is. And we're privileged to observe it, to study it, to try to understand it, even when it refuses to fit into our neat categories, even when it violates our predictions, even when it shows us something we thought was impossible. That's science, not finding answers that confirm what we already believe, but discovering truths that force us to revise everything, to think bigger, to imagine more, to accept that nature is always one step ahead of our understanding. The bizarre exoplanets are that step. They're nature's way of saying, you haven't figured it out yet. Keep looking, keep questioning, keep exploring. There's more out there than you can possibly imagine, and we will keep looking, because that's what humans do. We explore, we question, we reach toward the unknown, even when it's daunting, even when it challenges us, even when it reveals how little we actually know. The universe is vast, ancient, full of wonders we haven't discovered yet. The bizarre planets we've found are just the beginning, a tiny sample of the cosmic diversity waiting to be revealed. Somewhere out there is a planet stranger than anything we've imagined, a world that will force us to rewrite textbooks, revise theories, reconsider fundamental assumptions about how reality works. And we're going to find it, because we're building the tools, developing the techniques, training the scientists. Humanity is just getting started with this exploration. The darkest planet exists. The brightest planet exists. Planets rain iron. Planets rain glass. Planets made of diamond orbit stars made of gold. Worlds drift alone through the void. Others orbit two stars, or failed stars, or dead stars. Some have polar orbits, asymmetric atmospheres, impossible densities. Each one expands what we know is possible. Each one is a gift from the cosmos, a lesson in creativity, a reminder that the universe is stranger than we can think. So when you look up at the night sky, remember this: those points of light aren't just stars. They're planetary systems, worlds orbiting in configurations we're only beginning to catalogue. Some of them are bizarre beyond description. Others are Earth-like, quiet, stable, possibly harboring life. We don't know yet which is more common, but we're finding out, one discovery at a time, one bizarre planet at a time, one revelation at a time, and each one brings us closer to understanding our place in this strange, magnificent, endlessly surprising cosmos.